All right, young chemists, it is Mr. Ball. We are doing our first portion of our e-learning situation. I'm going through the last portion of our lecture in Chapter 7. So feel free to follow along, take notes, play this at 1 1/4 speed if it helps you out. And you also have these lecture notes as well already, but I'm just going to try to augment as best I can. Also, YouTube only allows for a 15-minute upload, so I have my timer set so I don't go over so that we can do this in segments if we have to. But we're going to go ahead and dive right on in. So let's look at some periodic trends in atomic properties. We've developed an understanding of electron orbitals, right? And I'm actually going to send you out a video here pretty soon about those electron orbitals and giving another look at them with kind of a quirky scientist guy on YouTube that I am really enjoying. But we can also look at other atomic properties depending on these orbitals. So there are things that we can find out like ionization energy, electron affinity, and how big the actual atom is so that we can actually know all this information based off of where an atom is on the periodic table and how many electrons it has. So the first thing we'll look at is the ionization energy, which is the energy required to remove an electron from a gaseous atom or ion. So if we've got this gas and we remove an electron for it, that requires energy, right? So we assume that the atom is always in its ground state. That's kind of our assumption going forward in intro level chemistry. And these are some of those energies required to remove several electrons from, our example is an aluminum atom. And these are examples of removing electrons one after another. So here we go. We've got our first electron removal, takes 580 kilojoules per mole. Second one, 1850, 2740, and then, 11,600 kilojoules per mole. Okay, so we're going to talk about what all that means here. So through this information, we can observe that the electron with the highest energy or the furthest shell from the nucleus will always be removed first. And this is called the first ionization energy, or I1. So this electron right up here, you got this fancy little laser pointer, that's the first one to go because it's the furthest away from the nucleus, right? It's hanging on with the least amount of strength. So its ionization energy is the lowest. Okay, and so we call that the first ionization energy. In this case, the electron comes from the 3p orbital, which is right there. You can see the electron configuration of aluminum. Okay, so we're taking away that p electron right there. Zoom and laser pointer. All right, so we're taking away that p electron. After the removal of that one, the second removal comes from the 3s orbital, and we call that I2, and it's going to be larger. The energy required will be larger than the first, and this is mostly because the new charge of the aluminum ion, the nucleus has one more proton than the orbitals have electrons, so they are drawn more strongly to the nucleus, the electrons are. And this trend continues, right? So the more positive the nucleus becomes, or it's not becoming more positive, but it has fewer negative charges that are opposing those protons, and so they more readily grab on and hold on to those electrons as they are trying to be removed. So the energy required to remove them is greater. Another reason for the increase in energy is that, especially in aluminum, when we have the ion of +3, it now only has core electrons or electrons within a previously filled electron shell. So when you have 8 electrons in there, those ones, they like that noble gas configuration, so they do not want to be removed, and so it requires even greater energy. And Table 7.5 shows this clearly as it shows the enormous jump of ionization energy to remove the core electrons. Okay, so where that line, that little stair-step line is, for various elements, that increase of energy required is pretty vast, right? You're jumping by several thousand kilojoules per mole. in every case, rather than just a jump of maybe a couple hundred or maybe 1,000 or so. So there's a example of removing the energies required to remove those. All right, and notice as we move from left to right on the periodic table, the ionization energy increases. We also observe another interesting trend. By viewing group 1A or 8A elements, we can see that as we go down the periodic table, the ionization energy decreases. And this is mainly because of the increasing size of the atom. Each electron is farther away from the nucleus, and space decreases the electric pull of pull P-U-L-L of the protons and the electrons, right? So as they're further away, the attraction between those positive and negative items becomes less, all right? So here you go. All right, here's another graphic too to show that trend. You can see that helium's energy required is pretty vast, whereas up here, something like cesium is very, very small, right? The energy required to remove those electrons. Notice also though, as you go to the right here, you're gaining or you're requiring more energy in order to remove those electrons. And you might think, well, why is that? Because there are more electrons there, right? Yes, but there are also more protons, which means that grasping of that first ionization energy is even greater, right? So that has something to play as well, where the theoretical distance of an electron from a nucleus in this area is relatively similar to the theoretical distance of an electron from the nucleus in this area. But here we have 7 more protons that are attracting that electron. Okay, so the energy required increases from left to right, and it decreases from top to bottom. So there are slight exceptions, though, between groups 5A and 6A, as you can kind of see as we move from the left to right. There's some weirdness that's happening there. Okay, so just note that as you're looking at nitrogen and oxygen, or phosphorus and sulfur, or phosphor and sulfur, even these two right here, you're getting a little bit of breakage of that rule that we've just talked about. So now we're going to look at electron affinity, the energy change associated with the addition of an electron to a gaseous atom. Okay, so now rather than taking an electron away, we're looking at, okay, what happens when we add an electron, right? So notice that we dictate electron affinity as a change in energy. And if the addition of an electron is exothermic, meaning that it gives off heat, then the electron affinity is actually negative. So when something's giving off heat, the number is negative, all right? This trend usually grows more negative from left to right on the periodic table, but there are many exceptions. It also grows slightly more positive as we move downward because the electrons being added are further from the nucleus. So similar to how that last graphic looked, right? This one is becoming more negative, meaning it gives off more heat as it goes towards the right, but it starts giving us off less heat as we move downward because they're farther from the nucleus. All right, the atomic radius. So now, similar to how orbitals and atoms cannot be exactly specified, it's kind of a flurry. The size of an atom also can't be exactly specified. Remember that most of an atom is empty space, right? The nucleus relative to the size of the atom is very minimal. The electron is that mouse turd flying around a stadium, right? We've talked about that before as well. So we can't exactly specify the space an atom takes up or the size that the atom is. So instead of being able to measure each individual atom, we measure the distances from proton to proton in bonded molecules. And this allows us to have very close measurements for the size of individual atoms. On the following slide, we'll see the sizes of different atoms and that it's slightly less than we might expect because the electron clouds slightly overlap one another when they're bonded. So the size is actually a little smaller than what we would expect, okay? But this is what we're looking at here. So notice the size of the atomic radius down there at the bottom left, right here of cesium, that's the biggest atomic radius that we can observe, right? And as we go over here, those radii get smaller and smaller, and between these two, I mean, that breaks the trend a little bit, but remember, we have the most amount of electrons right here, right? We require the most energy to eliminate these electrons. So if that's the case, why are they so much smaller than an atom like cesium? All right, so we're going to talk about that. You notice that the atomic radii decreased from left to right, and so it does seem counterintuitive, right? What we were just talking about. But it's because of electron shielding, okay? So one electron shields from another, and the increasing effective nuclear charge, drawing electrons closer to the nucleus, excuse me. So as you have more protons, they are actually sucking those electrons in tighter and tighter and tighter because of that electron affinity for the nucleus, okay? There we go. All right, so let's talk about some of the properties of a group, the alkali metals. This section summarizes the information that can be obtained from the periodic table. So here's the information. Okay, first of all, and this is just a general rule for the periodic table. First of all, groups represent elements that exhibit similar chemical properties. So it's the numbers and type of valence electrons that determine an atom's chemistry, right? They're all made up of the exact same elements. They all have protons and neutrons and electrons that are all made up of quarks, but they react very differently from one another based on the number of protons. Or excuse me, the number of electrons, pardon me. So the electron configuration of any atom can also be determined based on its position on the table. Remember, the S, P, D, and F blocks that we looked at earlier in this PowerPoint presentation, where groups 1 and 2 are the S block, groups 3 through 12 are the D block, you have groups 13 through 18 being the P block, and then your transition metals down there that are kind of taken out, that's your F block, right? So remember those as well. That's the electron configuration, okay? So here you go again, the lanthanide and actinides. That's what I was referring to down here. So we've got those are our F, D, P, and S. All right, so if you need a review over that, go back to slides prior. So then we also know that certain groups have special names. We've got the alkali metals in group 1A, the alkaline earth metals in group 2A. We have our transition elements, also known as transition metals. Then we have our non-metals, those green ones, really we can classify kind of as non-metals, halogen gases, and noble gases. Then you've got your lanthanides and actinides as well. Number 4, the most basic divisions of elements is in metals and non-metals. So metals tend to give up electrons, right? This is a review of bonding in general. Metals tend to give up electrons and form a positive ion or a cation. They generally have low ionization energies and are on the left side of the periodic table. The less ionization energy an atom has, the more likely it is to bond, so they bond very readily. Then nonmetals, they tend to gain electrons rather than lose them when bonding, meaning that they have the most negative electron affinities and ionization and large ionization energies. They're on the top right side of the periodic table. The most reactive are on the upper right, as long as they're not noble gases, because those gases are unreactive. And then the elements along the long division line exhibit both metallic and nonmetallic properties and are called metalloids or semimetals. Here's a visual representation of each of those things. We've got our metalloids over here on the right side in blue. There. You have your nonmetals up here, and then your metals are just about everything else. And lanthanides and actinides are kind of considered their own things, as they do some funky stuff as well. There you have it.